Welcome students. So today we are going to discuss about complex roots of characteristic equations. So what is the starting point? The starting point is you are starting with a homogeneous differential equation a y double prime plus b y prime plus c y equals to 0. Here a, b and c are constants. And the goal is to find the fundamental set of solutions for this homogeneous differential equation. Now, as we saw in last time from 3.2, we'll postulate that y equals to e to the power rt is a solution for some values of r. So let's work this out. So we have y equals to e to the power rt, then y prime is going to be e to the power rt times r, and y double prime is going to be r square e to the power rt. Now, if you substitute that in the differential equation, you will get a r square e to the power rt plus b r e to the power rt plus c times e to the power rt equals to 0. Now take e to the power rt common, so you get ar square plus br plus c equals to 0. Now, in this case, you can say that e to the power rt is a solution to above dE differential equation if and only if ar square plus br plus c equals to 0. Now, so this equation is called the characteristic equation. So, characteristic equation for of a y double prime plus a by prime plus cy equals to 0. So this is called the characteristic equation. And now based on the roots of characteristic equation, we can find out the solution to the given second order homogeneous differential equation with constant coefficients. So let's move to that. So now we need to find out r from this equation. So now there are three cases when we are solving this quadratic equation. We get ar square plus br plus c equals to 0, and there are three possibilities for the roots. So one is both the roots are real and distinct. For in that case, you will have r1 equals to minus b plus or minus b square minus 4ac over 2a. So since there are two solutions, let's call one of them as one with the plus sign, and r equals to minus b plus or minus, sorry, in this case we'll choose minus b square minus 4ac over 2a. Yeah. So and your solutions are form y1 is e to the power r1t, y2 equals to e to the power r2t. Okay. Now consider the second case that both of these roots are same. In that case, we have b square minus 4ac is 0, and we have both the roots are r1 equals to r2 equals to minus b over 2a. Now the second case is that the roots are complex, so we have b square minus 4ac is less than 0. That is when the quadratic equation will have complex roots. So I can write b square minus 4ac as what? So square root of b square minus 4ac as minus 1 times b square minus b square plus 4ac over, so this is going to be, if you, what is square root of minus 1 is, if you take square root of minus 1, you get I, so you get I times b square minus b square plus 4ac. So when you plug it in this this solution, you will get the solutions are of form minus b plus or minus b square plus 4ac over 2a, and here you have I. So now we want to separate it into two parts, the real part and the complex part. So let's, for the sake of brevity, write lambda equals to minus b by 2a and mu equals to minus b square plus 4a by 2a. So both are real numbers. Both are real numbers. And you get R1 equals to lambda plus I mu, and R2 equals to lambda minus I mu. And we'll see how does the solution looks like when we put this back into the solution. So let's deal with those cases, all these cases one by one. So if the roots are real and distinct, we have already handled this case partially. We have already shown that they form a fundamental solution. So let's see, we have solution y1 equals to e to the power r1t and y2 equals to e to the power r2t, and r1 and r2 are two distinct roots of the quadratic equation. Which quadratic equation? A r square plus br plus c equals to 0. Now, are these set of solutions fundamental? For that, we have to compute the Wronskian. So recall, what is your Wronskian? So you want to compute Wronskian at t, and you want to show that it's non-zero at some point, right? So this is going to be determinant of y1. Recall, it was y1, y1 prime, y2, y2 prime. So this is going to be determinant of y1, which is going to be e to the power r1t, y1 prime, which is going to be e to the power r1t times r1, chain rule. Here we'll have e to the power r2t, that is our y2, right? And the derivative of that is e to the power r2t times r2. And then when you compute determinant of this, it's going to be e to the power r1t times e to the power r2t times r2 minus e to the power r2t times e to the power r1t times r1. Now you can take these guys common, so I'll combine them together. So you have r1 plus r2t times r2 minus r1. Now note that this is not 0. Why? Because exponential is never 0. And since r1 is not equal to r2, this is also not 0, since r1 is not equal to r2. So therefore, in this case, we have y1 and y2 form a fundamental set. So is the fundamental set. And then the general solution is given by, the general solution is y of t equals to c1 y1 plus c2 y2, or c1 e to the power r1t plus c2 e to the power r2t. Okay. Now, let's move to the, so this was case one. Now I'll deal with case two, and then we'll deal with case three later on. So let's deal with case two. So sorry, case three. The case two, that these two roots are equal, R1 and R2 will be dealt separately in the next section. But let's deal with case three now. So in case three, recall the Euler's identity, e to the power x plus iy is e to the power x times e to the power iy. And this part is the Euler's identity. What part is the Euler's identity? E to the power iy is same as cos y plus I sine y. Yeah, this identity of writing e to the power iy as this is called Euler's identity. Yeah, named after Euler, famous German mathematician, right? So now, so we have this, and so note that all rules of real exponent apply to the complex exponents as well. So that will help us in trying to simplify the solution. So we have R1, as we saw earlier, is lambda plus I mu, and R2 equals to lambda minus I mu, where your lambda was minus b over 2a, and your mu is square root of minus b square plus 4ac over 2a. Now you may see, oh, well, generally it's b square minus 4ac, but recall you took out minus sign out to get I, right? So in that case, the solution is given by y1 t equals to e to the power r1t, which is e to the power lambda plus mu I, or I mu t, and y2 is given by e to the power r2t, which is same as e to the power lambda minus mu I t. Again, we need to check the solution is fundamental. Recall, why are we checking the solution is fundamental? Because if you recall from the previous discussion, if you get a fundamental set of solution, the linear combination of those fundamental set of solution gives you all the solutions. Yeah. So the idea is to how to get all the solutions, right? So now we want to show that these are fundamental. So let's go and do that. So again, we need to compute the Wronskian to determine whether it's fundamental solution or not. So determinant of, again, y1, so y1 is e to the power lambda mu I t, and derivative of this, again, the complex derivative works in the same way. You will have lambda plus I mu, or mu I, e to the power lambda plus mu I t. And then we have e to the power, so y2 is what? E to the power lambda minus mu I t, and then the derivative of that is the constant comes out here, e to the power lambda minus mu I t. Now we want to compute the determinant. Determinant is a, b minus, so determinant of this is going to be the determinant of, recall, determinant of a, b, c, d is ad minus bc. So I'm going to do the same computation here as we did earlier. So we have e to the power lambda plus mu I t times e to the power minus mu I t times lambda minus mu I minus lambda plus I mu e to the power lambda plus mu I t times e to the power lambda minus mu I t. Okay, so now out of this, what is, we can take these two guys as common. So we get what? We get e to the power lambda plus mu I t times e to the power lambda minus mu I t, and in bracket you'll be left with lambda minus mu I minus lambda minus mu I or I mu. So lambda and lambda will cancel and the top will simplify. So how will the top simplify? The power will simplify. You add the powers up, you will get e to the power lambda t plus lambda t. So 2 lambda t mu I t minus mu I t. So 0 for that contribution. Minus mu I t minus mu I t means minus 2 mu I. And note that this is not 0 because lambda is real. And since the roots are distinct, mu is not 0. Otherwise, the root won't be complex, right? Mu is the part which is giving the complex part to the solution, right? So since mu is not 0, it doesn't matter if lambda is 0, but since mu is not 0, the whole thing is not 0. So this implies the Wronskian is not 0, and these solutions form the fundamental set. However, we are interested in avoiding the complex numbers or complex valued function y1 and y2. So we'll devise a new set of fundamental solution. Now note that if you take linear combination of y1 and y2, so let's take a new solution, be half y1t plus y2t, and second y2 equals to half 1 by 2i actually y1t minus y2t. So superposition principle tells us that if you take any linear combination of y1 and y2, is also going to be the solution. So we got these as solutions as well. Now we want to show that these solutions are fundamental as well, right? Now, why are we interested in this? Because you can see that these solutions are not going to be complex. Okay, so let's deal with this quickly. So let's first show that these solutions are not, sorry, these solutions are also fundamental. So we want to show that these solutions are fundamental. So first of all, so now how do we show that these solutions are fundamental? Well, one way is to look at Wronskian, right? You can show that Wronskian of these two is non-zero. That's one way. Yeah. So one way is to show Wronskian of capital Y1 and Y2 is non-zero. Now, other way is the following. So notice that if you take Y1 plus I Y2, what do you get? You get half y1 plus y2. I'm not going to write t. It's clear that these are functions of t. I times 1 by 2i y1 minus y2. And you can see that this is going to be half y1. So these will cancel out. So let's see. Half y1 plus y2 minus 1 by 2 y1 minus y2. So now you can see that y2, half y2 and half y2 will cancel, minus half y2. And what do we get in this case? We'll get the solution is going to be y1, sorry, y1 and y1 cancel. You will have y2 and y2, so you'll get y2 here. Similarly, y1 minus I y2 is going to be half y1 plus y2 minus I 1 by 2I y1 minus y2. So we get half y1 plus y2 minus half y1. Oh, my bad. So this was plus sign here. So this would have been plus. In that case, I do get y1. In that case, I have y2. I do get half y1 minus half y1 gone. y2, half y2 minus of minus half y2, which is plus half y2. So that will make it y2. So we get what? We get that this is equal to y2. So you have shown, so since y1 and y2 are fundamental set, and they can be written as linear combination of these capital Y1, capital Y2, we get capital Y1, capital Y2 is also fundamental set. Yeah. So essentially here, what you're proving is that any solution can be written as a linear combination of capital Y1 and Y2. And how are you showing that? You're saying the following. You're saying this Y1 and Y2, these Y1 and Y2 themselves can be written as a combination of capital Y1 and capital Y2, right? So therefore, we get Y1, capital Y1 and capital Y2 are the fundamental set of solutions. Because any solution is, so you should think about it in the following way, any solution is a linear combination of Y1, okay, small y1 and small y2, and that in turn is a capital, that is in turn a linear combination of capital Y1 and capital Y2. So that basically makes it a fundamental set of solutions. Now, let's see, why did we do this? We did this because the solution becomes real. So we should check that. What do we get? We get, let's look at y1 first. That does it really becomes a real solution. So note that you had this as e to the power lambda plus I mu t plus e to the power lambda minus I mu t. Now this will become half e to the power lambda t e to the power I mu t plus e to the power lambda t times e to the power minus I mu t. Now, out of these, I can take e to the power lambda t common. So what do I get? I get half e to the power, let's write down here, half e to the power lambda t common. So e to the power lambda t common because multiplied in both of them. What is e to the power I mu t? It's going to be cos of mu t plus I sine of mu t minus, sorry, plus cos of mu t minus sine of mu t. And you can see that these cancels off. And what do you get? You get half, and this will add to 2. So that 2 and this 2 will cancel. So we have e to the power lambda t times cos of mu t. And which is what? Is real. Right? Why is it real? Because lambda t is real. E to the power lambda t is real, and cos mu is also real. So cos of mu t is also real. So you have shown that y1 is real. It's not complex. Yeah. Similarly, you can show that y2 is e to the power lambda t times sine of mu t, and that's also real. So therefore, what do we get? We get y1 and y2 give fundamental set of solutions set of real solutions for DE, for the differential equation, where a y double prime plus a y prime plus cy equals to 0 when roots of characteristic equation are complex, right? So we managed to get a real valued function. Now let's look at an example. So consider the following initial value problem. So we have 6y double prime minus 8y prime plus 145y equals to 0, and y of 0 is 0 and y double prime of 0 is 1. Now note that, recall, for second order differential equation, you have to be given two initial conditions to get the proper solution, right? So now let's first find the characteristic equation. So characteristic equation is simply replacing y double prime by r square. So what are you postulating? The solution is of form y equals to e to the power rt, right? Minus 8y so we get this quadratic equation as the characteristic equation. Now here, if you want to use the quadratic formula, a is going to be 16, b is minus 8, and c is 15. So we get r, before r is going to be 8 plus or minus square root of b square, which is 8 minus 8 square minus 4. A is 15, C is, sorry, A is 16 and C is 15. So A is 16 and this is 15 divided by 2 times A, which is 2 times 16. The denominator is going to be 32, 8 plus or minus square root of 64 minus, so if you do this on calculator, you'll see that the answer is 9216, and then the answer comes out to be 1/4 plus or minus 3i, right? So now let's determine the general solution. So we have lambda equals to 1/4, and mu in this case is going to be 3. So y1 is e to the power t by 4 times cos 3t. Why? Look at the solution. y1 was what? E to the power. If you look at this here, y1 is this. So e to the power lambda is 1/4 and mu is 3. And that's why the solution is e to the power t by 4 times cos 3t, and y2 equals to e to the power t by 4 times sine 3t. So these are the solution, and the general solution is a linear combination of this using superposition principle. So C1 e to the power t by 4 cos 3t plus C2 e to the power t by 4 sine 3t. So this is a general solution. Now you want the unique solution which comes because of the IVP, the initial value, right? So because so for that we need to look at the first condition. So y of 0 is 0. This is what is given to us, and what is the other thing given to us? Y prime of 0 is given to us as, let's go up and check. Y prime of 0 is given to us as 1. I'm going to write that here. So now this implies when I put 0 in this equation, I get C1 cos 0 is 1. So 1, or let's just put e to the power 0 cos of 0 plus C2 e to the power 0 sine of 0, which is going to be C1 cos 0 is 1, e to the power 0 is also 1, so C1, but sine 0 is 0, so C1 equals to 0. Right? Similarly, y prime equals to 1, so we get this. When I take derivative of this solution, I get t by 4. What is the derivative of this? So we have to find that out. So derivative of this is going to be, so either I take whole y prime is 0, or I should work with the following. So both of this updates my solution to be y of t is what? C1 is 0, so C2 e to the power t by 4 sine 3t, because cos C1 became 0 right here. So now once I have that, I'll apply y prime of t. This gives me y prime of t is going to be C2. I have to use product rule. So e to the power t by 4 times cos 3t times 3 plus e to the power t by 4 times derivative of t by 4, which is 1 by 4 multiplied by sine 3t. And we get y prime of 0 equals to 1. This implies, so C2 e to the power 0 cos 0 is 1. So cos 0 times 3 plus e to the power 0, 1 by 4, sine 0 is 0. Let me just write that. And this turns out to be 1. So what do I get from here? So I get C2 times 3 plus 0 is 1. So C2 equals to 1 over 3. So what is the solution to? So the solution to IVP, to given initial value problem, is y of t equals to 1, what? C2, which is 1/3 of e to the power t by 4 times sine 3t. And that is your answer. So this is how we solve an initial value problem with the complex roots. For the real roots, we have already seen when they are distinct. We have already seen that in 3.2. Now, next section is about when the roots are real, but what? But they are same. That means the roots are not distinct. Thank you for your attention.